ME347 Example 20. For this problem, use the same system described in Example 19 and the same pump family, which is the Peerless 4AE12 pump family operating at 1750 RPM. For Part A, determine the operating conditions for the 9.5-inch diameter pump operating with this system. For Part B, based on this operating point, find the pump operating speed required to deliver a scaled flow rate of 430 gallons per minute. For Part C, calculate scaled head, power, and efficiency for the scaled speed calculated in Part B. For this problem, we will need to make the same assumptions made to calculate the system curve in Example 19. These include the following. First, we assume steady, constant property flow of an Newtonian fluid, which is water at 60 degrees Fahrenheit. Second, we assume that the water in the large tanks has a constant height, that is open to the atmosphere, and that the velocity at the top is approximately zero. Third, we assume fully rough turbulent pipe flow near the operating conditions for the pump. Let's begin by looking again at the schematic diagram from Example 19, which shows water being pumped upwards from a lower tank to an upper tank. The water in the lower tank first enters the piping through a reentrant entrance with a loss coefficient of 0.78. Then it goes through 10 feet of piping and 1 elbow before the pump suction inlet. After the pump discharge, it goes through 40 more feet of piping and 1 additional elbow before flowing into the upper tank through an abrupt exit with a loss coefficient of 1.0. For both of the elbows, the minor loss is given in terms of an equivalent length of straight piping. Note that the pipe has a diameter of 3 inches, a roughness of 0.0050 feet, and a total length of 50 feet. Also, the change in elevation of the water before the pump is 5 feet, and the change in elevation after the pump is 20 feet, so the total elevation change is 25 feet. Note that this data was used in Example 19 for Part A to find the system curve and for Part B to find operating conditions for the 11-inch diameter pump, as shown. Note that the scaled flow rate we are using for this problem corresponds to the operating flow rate for the 11-inch diameter pump. For Part A, determine the operating conditions for the 9.5-inch diameter pump operating with this system. We begin by again plotting the system curve on top of the pump performance curves as we did in Example 19. Recall that each pump will operate at the intersection of its pump curve with the system curve. For the 9.5-inch pump, our new operating point shifts to the left, resulting in a lower flow rate of 370 gallons per minute and an operating head of 88 feet. The efficiency also drops slightly to 71%. Next, we look at the additional performance curves for the Peerless 4AE12 pump family. At our operating flow rate of 370 gallons per minute, we get that the net positive suction head required is 6.3 feet and the operating power is 11 horsepower. Finally, a summary of the operating conditions for our 9.5-inch diameter pump is given. Note that the operating head is shown being calculated using the system curve. Of course, this value should be the same as the one that can be read at the intersection of the pump curve and the system curve. For Part B, based on this operating point, find the pump operating speed required to deliver a scaled flow rate of 430 gallons per minute, which recall is the operating flow rate for the 11-inch diameter pump. From a dimensional analysis of pump performance, we know that to scale the speed for the pump, we need to match the flow coefficient defined as shown. To simplify this equation, first note that the ratio of the angular velocities and the ratio of the pump speeds are the same. Second, the diameter is constant. Thus, we get that the ratio of the pump speeds is proportional to the ratio of the volumetric flow rates. Solving for our scaled operating speed, we get 2034 RPM. For Part C, we are solving for the remaining pump operating conditions for the scaled speed calculated above. Again, from dimensional analysis of pump performance, we know that if the independent flow coefficient matches for two different operating conditions, then the remaining dependent dimensionless parameters must also match. In other words, for conditions where the dimensionless flow coefficient is the same, the flow through the pump will have similar kinematics. To begin our calculations, we solve for the scaled head by matching the head coefficients. We now get that the ratio of the operating heads is proportional to the ratio of the square of the operating speeds. This results in a scaled head at the operating point of 119 feet. Next, we continue Part C by calculating the scaled power for the scaled speed calculated in Part B. For this calculation, we now match the power coefficient. This time, we get that the ratio of the operating power is proportional to the ratio of the speeds to the third power. This results in a scaled power at the operating point of 18 horsepower. Note that for the 11-inch pump, the power required is 16.3 horsepower. Thus, it may be less expensive to buy the bigger pump depending on electricity costs. Finally, for Part C, calculate the efficiency for the scaled speed calculated in Part B. Note that because the efficiency is already dimensionless, the scaled efficiency is the same as the efficiency at the original operating point. For the last slide, I have included plots of the original and scaled pump curves for the two different operating speeds, along with the system curve. From this plot, we can see how the operating point shifts to the right, increasing both the operating flow rate and head as the pump speed is increased.